some problems to think about with each of those questions. So here we go. The first question, what is the basic factoring technique? So this is the type of problem I'm referring to. And then what must you do before you can do basic factoring? So here's a problem I'm thinking about, such as, and then it says, what is factoring by grouping? So here is a problem with factoring by grouping. So we'll say that one. And then what is the difference of squares? How does that work? Such as x squared minus 36. And then if the first term is not 1x squared, what is the clever trick you must do? So let's say that you had a problem like 3x squared. So we'll do 8. There we go. So if a equals 1, or a is not 1, there we go. And then finally, how do you simplify a root? So go ahead and read through those questions either on your own or with your partner. Go back into your notes, find your notes on those problems, and we'll start in 2 minutes.
Right. And then if there's 3, you know what I mean, instead of 4, and you're trying to group it, like should it? What is basic factoring? It could be either one or explicit.
I made a note to myself to get some rags.
Or you can factor in.
Basically, yeah, Rachel's
Like if there's like you can like
And then have a, has to be an expert.
You transformed over to the racks now?
Oh, I'm a total convert. I told Shannon.
That's just like the first square. Where you have like an explicit.
What is the difference of squares?
Oh, okay.
The difference of squares is when I know this one. And when you multiply the front to the right,
Okay, well, you're all having very productive conversations, but it's been a few minutes, so let's review this together. Let's start with the first one. What is the most basic factoring technique? What's the usual basic question you ask when you're confronted with the simplest of all factoring problems? What question do you ask?
Is it factorable?
It's what?
Is it factorable?
Well, that's true. I mean, we're wondering, are all of these factorable? But how do you actually do the basic factoring technique? You ask.
2 numbers that adds 12 and multiplies.
What 2 numbers multiply to make 12, and then that add to make 8. Yeah, very good. So in this particular case, you'd make your factor table for 12. You'd say, well, 1 times 12, 2 times 6, 3 times 4. And which one of them does Valeria do add up to 8?
6 and 2.
Yep. So 2 and 6, again, we call this the most basic situation because x squared has a 1 on it. You can simply ask what multiplies to make 12 that adds to make 8. And the numbers that you find, that is the answer. And you can immediately write down x plus 2, x plus 6, and you're done. So that's the basic factoring technique. You call that like lucky, right? Like, okay, that one was very simple to factor, no problem. What about, you know, this is still basic factoring, but what might you need to do first? Yeah, you might need to take out a common factor and or also a leading negative. So in this case, we could divide out a 2 and we can divide out a negative. So if I take out the negative 2, first of all, you know you're dividing by 2, so that'd become a 1. That 16 divided by 2 is 8, 24 divided by 2 is 12. What happens to all the signs now? Yeah, they all change. Plus becomes minus, minus becomes plus. So now we have this, and we already know the solution to 1x squared plus 8x plus 12. We would end up with negative 2 times x plus 2 times x plus 6. And this right here we say is fully factored, right? So there's nothing else you can do to this. It's fully factored. Now, if this wasn't just an expression floating in space, but we actually made it an equation equals 0, then what could we do? Right, yeah, if we do set it equal to 0, then what?
You divide the negative 2.
Well, that's true. You could go ahead and divide off the negative 2 just to get rid of it, so you don't see it anymore. And now it's completely factored, and we could use what rule? The zero product rule. And that, yeah, that states that this times this equals 0, so either this is 0 or this is 0. And then we're actually able to come up with our final solution of negative 2 and negative 6. What do those two numbers represent in terms of this equation?
The x-intercepts.
Yeah, they're the x-intercepts. So if we went back to the original problem, well, this way, negative 1, 2, there's an x-intercept, 3, 4, 5, 6, there's an x-intercept. And this is an upside down parabola, so we know that our original graph looks something like this. Okay? So this is wonderful. This is a great example of showing how we factor and then why we factor, and that is to find x-intercepts. Now what about factoring by grouping? How does that one work? How, Omar?
So like the first portion would be squared plus squares,
And then?
and then negative 2 is negative.
You're right. The negative goes with the 2. So when I put that in parentheses, what do I have to remember to put right here? Yeah, plus sign, because this is still an addition problem. So then what do I factor out of here, Hector?
You factor out the square root, no, not square root of x.
Yeah, you can take out an x, so you have x plus 4. And then, Emily, what do I take out of here?
2
A 2 and
and negative.
the leading negative. So we bring out the negative 2, leaving behind what?
X and
Yeah, x and 4. Now, what's really important that we see now? Yeah, they're the same. It has to be the same. If it weren't the same, you would say can't be factored. But since they are the same, one of your factors is x plus 4, and what's your other factor?
X minus 2.
Yeah, the bits left over out front, so x minus 2. Is this answer correct?
Yeah.
We hope so. How do we know if it's correct? Yeah, you'd have to FOIL it out and see if it works out. And in this case, it does. If we FOIL that out, we get first x squared, outer minus 2x, inner plus 4x, last minus 8. Combining like terms, we'd have x squared, plus 2x minus 8. Going back to the original problem, if we just combine these terms, 4x minus 2x, what do we get?
2x.
Yeah, just 2x. So this is indeed equivalent to the original. Okay?
And then if you didn't have 4 terms, then you break up the.
Right, that's what we'll do in this last one. Yeah, for sure. Okay, then what was difference of squares? Right. So long as this number 36 is a square number, which this is, then you see x squared minus 6 squared. Those are the two numbers you're going to use to write down the product of, I don't remember the word. Conjugate. Conjugates, yeah, these are conjugates. So one is plus and one is minus. Okay, now, traditionally, we only bother using the difference of squares if this is a square number, because we want to factor it into whole numbers, and that way we know that x-intercept is a whole number. However, just so you know, you can use it even if it's not a square number, like 35. It's not a square number, but I can write it as a number being squared. For instance, I could write x squared minus root 35 squared. Because what happens when you square a root? When you square a square root, it cancels out and you just get 35. So now remember, whatever numbers are being squared go inside as conjugates. So I've got an x, I've got a root 35. So I could factor this as x plus root 35 and x minus root 35. Does anybody really do that? Not so much, right? But it's possible. I mean, you might see that in a problem where they expect you to get all the way down to your final x-intercept. So again, if that was equal to 0, I could now say for sure, set that equal to 0, set that equal to 0, and my x-intercepts would be x is equal to plus or minus root 35, which is some decimal value like 5.9123 or something. Okay, last one and the most, the one that takes the most effort is this basic factoring, like that. Is this basic factoring? Why not?
It's a 3.
It's a 3. So we cannot just say what multiplies to make 5 that adds to make 8. If you tried, you would fail, because the only thing that multiplies to make 5 is 1 and 5, and did they add to 8? No. So you can't just use the basic factoring. Instead, what do we have to do? You could try to factor out the 3, but it doesn't.
Split the 8.
Right. And my question was, if the first term is not 1x squared, what, sorry, excuse me, what clever trick do you have to do? And that is rewrite 8x as 2 terms so that you can factor by grouping. So do we just arbitrarily rewrite 8x as like 1x plus 7x or 2x plus 6x? Yeah, we multiply the 3 times the 5 to get 15. And then we do the factor table, 1 and 15, 3 and 5. And we look for the 2 numbers that add to 8, which is the 3 and 5. So now we just rewrite the middle term. And that's really the core of this whole method, is to rewrite the middle term, 3x squared plus 3x plus 5x plus 5. And now you can factor by grouping. And away you would go, you'd factor by grouping and then finish the problem. Okay, so these are all of our factoring techniques, which essentially for the rest of your life, you want to have those in your back pocket. You know, have them written down on a sheet of paper that you carry around with you. Take a picture on your phone and leave it on your phone, and then put that picture in your favorites, and then you can always go back and say, oh my gosh, what was that factoring technique? Exactly, post them on Instagram or TikTok. Isn't that like the new hip thing? What? No? Have you heard of it?
Well, I've heard of it, but I feel like I'm a little too old to.
Yeah, I think I'm too old for that. I'm even too old for Instagram. I mean, I don't know what that is. Okay.
MySpace?
No, I do Facebook.
I'm just kidding.
Yeah. All right, so now what were we just saying? Yeah, so you want to remember all these factoring techniques because you use them again and again. You use them in this class, you use them in your calculus classes. You end up factoring quite a bit. Okay, last question. How do you simplify a root? So let's say that I have the square root of 75. So first of all, you cannot square root 75 cleanly. That would turn out to be some decimal approximation, like 8.6713, repeat, on and on and on. So how do we simplify it? Okay.
You find like the closest number to the left, right? Or
well, first we'd want to write down our list, right, of square numbers, 1, 4, 9, 16, 25, 36, 49, 68, or 64, and 81. So we know 75 would be right around here. And keep going, Gabe. You're saying to
go to the left.
Start working to the left.
See which one multiplies into it if you divide.
Yeah, find the first one that divides into it, which is 25.
Yeah, it divides.
And how many times does 25 go into 75?
3.
3. So you rewrite it as 25 times 3, and then we're allowed to break that root apart into root 25, root 3. That's the product rule for roots. And now root 25 is a clean square root. You can actually square root 25 and get 5, and then you're done. Why do we say that this is a simplified version of that? Because it took more work. It wasn't simpler for you, but we call it simpler. Why?
What would it be if you switched the numbers?
If you did root 3, root 25? Is that what you mean?
No, like 3 is outside, 5 is inside.
Well, that would be a different problem. If you had 3 root 5, that would be the same. 3 is really the square root of 9. And the square root of 9 times the square root of 5 would be the square root of 45. And that would be a completely different starting problem. Yeah, good question. Yeah, it definitely has to be this order. Okay, so why do we call this simplified?
Smaller.
Yeah, smaller number in the root. A smaller number in the root.
It still represents.
Right, if you type it in your calculator, it's still going to be exactly the same value.
Okay. Oh, okay.
Yeah. Okay. Well, wonderful, folks. So these were the main ideas we talked about last time. All very important concepts. So where are we at? Today is February 6th. We're doing sections 2.6 and 2.7. We are going to wrap up 2.5. I just want to do like one more quadratic formula problem with you. There's a couple good ones in there. And then you have your test next week. So just to clarify, your test is on Monday. You will see that on Canvas, I posted an announcement where I titled it something like Solution Keys. And within that announcement, you have solutions for the in-class notes that we've taken. You also have solutions for the practice test. So you can go home this weekend. Oh, I also posted the practice test, so you can get an extra copy. Everybody should have a copy. You can print more. So then you can go home, you can take the practice test, compare it to the solutions. And then print out the practice test again. Do it again, and compare yourself to the solutions. Remember that all three of those things are due on Monday in the day of the test. Your chapter 1 notes, your chapter 2 notes, and your practice test. They're all due. And seeing as I posted the solutions for the practice test, none of you have an excuse not to turn in your completed practice test, which will be valuable experience for you in any case. Emily.
Is this one new or the other packet?
Great question. Your chapter 2 packet, which looks all official, 2.2, and then your chapter 1 packet, which looks all official. It has chapter 1. Well, it starts off with the chapter 1 notes. These are due as well as your practice test.
Okay.
Yeah.
And all those like square roots and
Those other ones I just gave to you as a gift. You can keep that forever. Give it to your children. Put it on your pillow. I won't collect it for credit.
Right.
These ones you can put in like under the pillow.
Yes.
All the knowledge.
Absolutely. Because if you put it on your pillow, you're more likely to look at it. And if you look at it again, you're more likely to remember it again. Exactly.
I was.
All right, so that's where we are. Monday, you get to use your calculator. You get to use your pencils, obviously. If you have any calculator questions, please email me your calculator questions, or please come see me in office hours.
I don't even know if it's possible, but allowed to put. See, I don't think that. So I guess what I'm trying to say is is there any way that we could put the formulas in the calculator?
If there were, that wouldn't be moral.
No.
Right? You're not supposed to take formulas in with you.
Oh, okay.
Yeah. So don't do that. But I will tell you this. Okay, first of all, the formulas, no. I'm not going to put those on the board. You have to memorize them.
Okay.
But my technique, when I'm a student, which I am, I'm in a math class right now, I study. I put the material right in front of me, right up until the minute the teacher gives me the test. So here comes the teacher. They're bringing the test to me. I have my paper right in front of me. They're about to come to me. I take my paper. I put it away in my backpack. I take the test. I immediately start writing down formulas.
Okay. So
Because you've got like 10 seconds, right, of short-term memory.
we can write it down.
Yeah, by all means. As soon as you get your test, write everything down. Yeah. Hector? Okay. Now, one thing I will say, okay, for all tests, I will help you with your graphing calculator. So if you're in the middle of the test and you're like, oh man, my calculator has an error, I can't get this to graph, just come up to me and I will help you work your graphing calculator. I will not show you how to solve a problem, but I'll show you how to graph something on your calculator.
now I have.
Yeah.
So when I do the homework, there's one problem that I typed in my calculator and the numbers were way too big. I couldn't see it on my calculator.
Right. So you'd have to change your window.
They did. So what?
On your calculator, and I'll show you, just see me before after class, you need to change your window so you can see more or less. Desmos is very easy. You scroll the wheel and you zoom in and out. Your calculator, you have to go into window and then change all the settings. But I'll show you how to do it.
There's 2 ways on how to fix the window.
Well, that's true.
So it's-
Yeah, and Lee could show you all that stuff as well. Yeah, because what are you going to say? Changing the values and then?
Yeah, and then going in and actually seeing which one you want to take. You can either zoom into it, you can box it.
I'll help you right after class.
There's all kinds of things you can do with the window itself. It's on your preference.
Yeah. All right, and in fact, we're doing an exercise today when we get to section 2, well, the last section on regression. We're going to see how to change our window. Okay, so I will tell you a joke, and then we'll get started. By the way, this is the last week for honors, so if any of you wanted to do the whole honors thing, to research a mathematician and write a biography and do a little extra math, you can still do that with me.
Is that a classic assignment or?
Yes, you do have to fill out a short application. It's just my class. You don't go anywhere else. It's just me. And then you agree to come see me in my office maybe once every 2 weeks. And then I just work you through the process. I help you through the process. Okay, is that everything I wanted to say? Yes, it is. So here's a joke. It's not on the screen. Here's a joke, a classic. Why were the ancient Romans so good at algebra? Why were the ancient Romans so good at why? Because x always equaled 10.
He's laughing, but we don't.
In Roman numerals,
Oh.
in Roman numerals, b is 5, and so it's just, no matter what problem they did, x was 10. Wait, I should have said what? Oh, I see. Yeah, x always equals 10. That's a good one. I only just learned that joke last year. I'm like, how did I go my whole life without learning that joke? All right, so this is where we left off. We were doing some quadratic formulas. We did which ones?
I think we did up until
We did. Well, that's good. We did 1 and 2 and
7.
7. Okay, great. So we did number 7. I would like to go ahead just to do one more. Let's go ahead and do 10. Let's do number 10. So we're going to think about this from the full perspective, okay? We're handed a quadratic, and it's 6x squared minus 12x plus 2. You remember one of the big questions we ask in this class is, every time you look at a function, you ask the question, what does it look like? Right, what does that look like? I mean, if you did bust out your graphic calculator, what would it look like? So at face value, what would it look like? Well, that's a good point we do that. It's parabola and it's facing up. So we know that it's a parabola facing up. How many solutions, or then again, how many x-intercepts could we have?
0, 1, and 2.
Yeah, either 0, 1, or 2, right? So the parabola could be up here and you'd have no solutions. The parabola could be here and you'd have 1 solution. Or the parabola could be here and you have 2 solutions. Do we know already, just by looking at this, which case it is? No, we don't know. Well, we know it's one of those 3, right? So we have some sort of an idea about what this looks like. And now our goal is to find the x-intercepts. So we're going to use the quadratic formula to do that. Remember, the quadratic formula, even though we write it as negative b plus or minus square root b squared minus 4ac going 2a, and we always just write x equals, it's really helpful if you write x int equals. Because that reminds you that the quadratic formula is solving for the x-intercepts. That's what you're finding. You're figuring out which of these 3 cases you're looking at. All right, so what are the values? We're looking at currently the values of a equals 6, is negative 12, excuse 2. Now, should we go ahead and do that problem? Use 6, negative 12, and 2? Or what could we do first?
Multiply 62.
Well, that would be if we wanted to try to factor.
Okay. So
Yeah, we could try to factor, but we're practicing the quadratic formula. So what can I do? We can take out a 2. I think that could be helpful, actually. We might as well. Let's take out the 2. If you factor out a 2, then you have 2 outside of, and now you're dividing. So 3x squared minus 6x plus 1 equals 0. And now what can I do with that 2? You just divide it off and it's gone. So the 2 is completely gone. And now we have this new, simpler, and by simpler we mean smaller numbers, quadratic. And the x-intercepts will be the same as the original, except now we have smaller numbers. So the fact that we're about to plug these numbers into the quadratic formula, we might as well make the numbers as small as possible, which we just did by factoring out. So taking out a common term is always a good idea. All right, so we have the formula there. A good best practice is always to write it empty. So I'm going to go ahead and write down my formula empty. So negative b plus or minus the square root of b squared minus 4ac all over 2a. And now we just go about plugging in all of our values. So go ahead and do that and start doing your computations. And remember, I suggest you do baby steps, just a little bit at a time. And get yourself to the point that you just have a single number under the square root. So what's that? Oh, that's right. Because look at, no, it's not. But why are you going to do it? Because it comes down to square minus 6x plus 1. Oh, wait. Well, that just means it's not factorable. That just means it's not factorable. That doesn't mean that there are no x-intercepts. That's very subtle, Omar. Very big point. If it's not factorable, that means you have to use the formula. See, there's only some quadratics that are factorable, and then you're like, oh, this is factorable, this is easy. But for a quadratic that's not factorable, the conclusion is you just have to go use the quadratic formula. Hey, very nice. Oh, I like your color code. That's super, yeah. Yeah, very nice. What's negative 6 times negative 6? What's a negative times a negative? Yeah, there you go. Perfect. All right, so I'm going to work along with you. So the first term, negative 6 is positive 6. And then on the inside, again, just baby steps. Negative 6 squared is 36, and then minus 12 all over 6. And then that brings us to 6 plus or minus 24 all over 6. Okay. So let's talk about that. What we just did was we just computed the quadratic formula. And if you stopped there, well, you know, I mean, you could stop there. 6 plus or minus root 24 all over 6. You type that into a calculator, it's going to give you an accurate result. But is that result simplified? Why is it not simplified? Well, okay, so that's a very interesting question. Can we cancel the 6's? That's one question, can we? Now that's another consideration. Can we simplify root 24? Is there a square number that goes into 24? Which square number? 4. So yeah, we can simplify the root 24. And then the question is, past those 6's, can we cross cancel the 6's? Is that what you want to do? Anyone want to take a guess about just cross canceling the 6's? Can we, can't we?
So we factor the part would just be like 2. That would be the common number for all 3.
What do you mean after you simplify, right?
Yeah.
Let's pretend for a moment that we can't simplify the root. Just can we cross cancel those 6's?
Yeah.
Yeah.
Well, let's find out. What if the problem was 6 plus 5 over 6?
Or would be 11.
The real answer that we know it to be would be 11/6.
Yeah.
If I went like that and called that 1 and 1, then I'd have 6 over 1, which is radically different from 11 over 6. So I can't. Yeah, we definitely cannot. Okay, but now the root 24, for sure we can simplify. So use some scratch space and say, well, 24, we all said that 4 goes into it. So that's 4 times 6. And so you break apart root 4, root 6. And then you have 2 root 6. So now, even though, you know, ostensibly we're like, hey, we just did the quadratic formula, a second process kicks in where you have to simplify. Okay? So what we just accomplished is the quadratic formula. And you can feel very satisfied with yourself. But now you have to finish simplifying. So now we have 6 plus or minus 2 root 6 all over 6. And again, here you might see all those 6's and be really tempted, like, ooh, I want to cancel out all those 6's. But the number inside the root is untouchable. You can't go canceling any whole number outside of the number in the root, because that's a root. But we can cancel something with the 2, the 6, and the 6. What goes into 2, 6, and 6? 2. Now, the most careful way to do that, like for instance, let me give you a for instance over here. Let's say that numerator, instead of being 6 plus 2 root 6, what if it was just 6 plus 2x? What would you factor out? Just factor out a 2, right? What would be left behind? 3 plus 1x? That's exactly what we're going to do in the numerator. So the 6 and the 2 are both divisible by 2. So we factor out a 2, leaving behind. Yeah, now I put 1 root 6. Could you just write root 6? By all means. I just put the 1 there to be a little more cautious. Now all that's over 6. Now what can we do? Yeah. Yeah, we're definitely allowed to simplify the 2 against the 6 now. And so what goes into both 2 and 6? 2. So 2 goes into 2 once, 2 goes into 6 3 times. And now we are absolutely done. The numerator is just 3 plus or minus root 6. And the denominator is just 3. Okay. You tell me. We were just talking, oh, I already erased it. We were just talking about can you just cancel those. And the example I gave was that. So that stays there. No, what was your question? Like this one?
Yeah.
Okay, to be fair, some people just do it like this. They say, hey, I've got all these whole numbers, and provided that there is that each term is divisible by 2, you could say 2 goes into 6 3 times, 2 goes into 2 once, and 2 goes into 6 3 times, and that would still give you 3 plus or minus 1 root 6 over 3. Is that what you meant?
Yeah.
That is legitimate. Yeah, that's fine. It's just that You know, if you feel comfortable with that technique and you know what you're doing, it's fine. But this way is the more legit way, where you're following the proper procedures for taking out common terms. Okay, so again, I just want you to appreciate, we started the problem, we did the quadratic formula, and got to there. That's quadratic formula. In the Moore system, when you're typing in your homework, Moore will accept that because it's accurate, it's correct. But is it simplified? No. Yeah, this particular problem we wanted to simplify. So yeah, there's two phases to a quadratic formula problem. One is just compute the quadratic formula. Two, you have to simplify the root, factor out any common terms, and simplify against the denominator. Yep, and then from there, like if you really wanted to write it down as two separate things, you would have on the one hand 3 plus root 6 over 3, which you could type in your calculator and get a decimal, and then 3 minus root 6 over 3, which you could type in your calculator and get a decimal. But for the most part, when the answer has a root, it's traditional just to leave it. Yeah. If you wanted the decimal approximation, that's what you do.
Simplify it.
Simplify, well, you just look. What did we do first? We simplified root 24 to root 6. Then, that was what I was saying with the game. Then we took out a common factor from the numerator, and then you simplified the denominator. Yeah. Yep. It almost seems mean because, I mean, the quadratic formula is challenging enough. You know, there's a lot of opportunities, mistakes, negatives. But then even when you do the quadratic formula, there's the second process that you have to do. So it's very patient, careful work. If you have any questions, we could talk more, but otherwise I think I'm feeling good that we covered a good amount of examples. Emily?
There's no common factor, just leave it.
Correct. If there was no common factor, you would just be done. So let's say that your answer came down to be 5 plus root 30 over 6. Root 30 is not simplifiable. It's not divisible by a square number, so you're just done. Yeah. Okie dokie. Well, we have all sorts of fun lined up. This next section is called Inequalities with Absolute Values in Quadratic Functions. Now, let's remind ourselves, what do quadratics and absolute values have in common? What's that? They do. They have the same number of solutions. If we go right back to how many solutions can you have, the absolute value function could be above, the absolute value function could be on, and the absolute value function could be, below. So you either have 0, 1, or 2 solutions. And the quadratic formula naturally lends itself to 2 possible solutions. Absolute values also naturally lend themselves to 2 possible solutions. And we'll talk about how. So I know that these notes packets give notes sometimes. Sometimes the notes are great, and sometimes I'm not as excited about them. We're not going to read those notes together. We're just going to go look at the first problem. Okay. I feel like I might as well do it right here. So let me erase. What does absolute value mean again? How far it is? Exactly. How far it is from 0. So let's all look at that first problem, number 1. And it says the absolute value of something is less than or equal to 4 units away from 0. And that's how you read the whole thing. You'd say, whatever's under my hand, whatever that number is, it's less than or equal to 4 units away from 0. So let's just look at a number line real quick. Where could the number under my hand be? Here's 0. Here's 4 to the right and negative 4 to the left. Where could my number be if it's less than 4 units away from 0? Yeah, it could be anywhere here, anywhere here. Could it be 4? Yeah. Because that's less than or equal to 4 units away from 0. Could it be negative 4? Yeah. And could it be anywhere in between? Yeah. So that's what we're saying. We're saying that 3x minus 5, whatever that value is, it better take on the value of somewhere in this shaded region. So we know that 3x minus 5 is somewhere in there. All right? Now let's be even more specific. On the one hand, like 5, I'm going to put 3x minus 5 over here for a second. I know that 3x minus 5 has to be less than or equal to 4. Is that fair? I know that 3x minus 5 must be less than or equal to 4. Because it's starting at 4 going to the left. Now come over here to this side. I know that 3x minus 5 must also be greater than or equal to negative 4. So that's the second thing I know. So 3x minus 5 must be greater than or equal to negative. And you'll notice it just produced two natural solutions, which are the two potential solutions if there are two roots. So that's what happens. You take this absolute value, you think about what it means that whatever's under your hand has to be less than 4 units away from 0, which means that the 3x minus 5 is either less than or equal to 4 or greater than or equal to negative 4. And that produces two separate inequalities for you to solve. So solve them. On the one hand, we have 3x minus 5, x is being multiplied by 3 and subtracted by 5, so I add 5. That gives me 3x is greater than or equal to 1, multiplied by 3, and x is greater than or equal to 1/3. That's one possibility. And then the other possibility, you solve it the exact same way. You got 5 on both sides. 3x is less than or equal to 9, divided by 3 on both sides. You'll notice the algebra was the same. We just ended up with two different answers. So now what does that look like? Another number line. We're saying that x had better be more than 1/3 or less than 3. And that's where x had better be. So x itself had better live in this interval between 1/3 and 3. And provided you choose a value of x in this interval 1/3 and 3, then 3x minus 5 is going to live in the interval between negative 4 and 4. It's an if-then statement. If you choose any x value between 1/3 and 3, then 3x minus 5 will be between negative 4 and 4. So somebody choose a value for us between 1/3 and 3. Make it easy. Between 1/3 and 3. Yeah, 1 is fine. Let's choose 1. If I go back to my original here, if I let x equal 1, 3 times 1 is 3, 3 minus 5 is negative 2, the absolute value of negative 2 is 2. Is 2 less than or equal to 4? Yeah. Yeah, so indeed, choosing any number in this interval will create the result that 3x minus 5 really is less than or equal to 4 units away from 0. Okay, so then what's the answer? This interval. This interval down here, which is the interval bracket 1/3 comma 3. That's the answer. Now I really appreciate that this whole process can feel confusing at first, because there's a lot going on. We begin the problem by setting up an interval for where 3x minus 5 could be. That allows us to create two separate inequalities to solve for x, which creates an interval where x could be. And then that is our answer. Valeria.
So if you have a 5 instead of a 4,
Yeah.
you set up the table, I mean, the graph 5 and negative 5? Okay.
Yeah, exactly right. Good question. Another question? Now, I'm going to tell you now, so we fully understood this. We're saying that we understand this process. We followed this process conceptually from the definition of absolute value. When I was a kid, and maybe this is how you saw it when you're in high school or junior high as well, is I was just told a purely mechanical process. I was told when you have an absolute value, here's what you do. You create two separate inequalities. You drop the absolute value symbols, 3x minus 5. You write it down exactly like it is. Then you drop the absolute value symbols and you switch and change. Switch and change. Is that what you remember? That's the mechanical process. And if you remember those steps, good. You can just follow those steps. That'll always work. But now I hope you see why we did that. Because this is way more interesting conceptually, that you can see why we have this mechanical process that works. So for instance, let's look at number 2. In number 2, first of all, it starts us off in a way that we're not ready to do work yet. What do we have to do? Yeah, we have to isolate the root and get it by itself, right? So, yep. So we need to add the 4 over to the other side. And now we have absolute value of 2 minus x is greater than or equal to 1. Now again, grade school, or elementary school, sorry, no one was doing this in elementary school. Junior high and high school, what would the teacher have told you? They would have said, write it down without the absolute value, write it down after you flip and change the sign, and then just solve both. That would be the routine. Okay? No. Because absolute value doesn't mean change signs. It means distance from 0. Yeah. Okay, so that's what the process would lead to. But let's actually, analyze it the right way. Let's analyze it the right way. Distance from 0 is more than or equal to 1 unit away. So the number under my hand, which we don't even have to worry about what it is, but whatever's under my hand had better be more than 1 unit away from 0. So what does that look like? Where can my number be? It can be anywhere over here, and it can be anywhere over here, because that's more than 1 unit away from 0. Can it actually be 1?
Yes.
Greater than or equal to. Can it actually be negative 1? Yeah. So that's just the definition of absolute value. The distance from 0 of this number has to be greater than or equal to 1 unit away from 0. So I've shaded where 2 minus x can be. 2 minus x can be over here. 2 minus x can be over here. Now, we can easily write down what these inequalities are. We're saying, from this one, we're saying 2 minus x has to be greater than or equal to 1. So you'd say 2 minus x has to be greater than or equal to 1. Now we're saying 2 minus x has to be less than or equal to negative 1. 2 minus x has to be less than or equal to negative 1. Did that produce the same result as our, memorized mechanical process? Yeah, it did. Now the good news is, am I going to be standing over your shoulder during the test? Hey, how are you getting there? I mean, you can just do that, right? You can just do that. But I really hope what you're taking away from this course is a deeper understanding of why this works. Okay, so once again, we solve. Now, 2 minus x, you have to be very careful with your algebra. This is x is being multiplied by negative 1 and adding by 2. So you subtract 2, and now we have negative 1x is less than or equal to negative 3. And now x is being multiplied by negative 1, so you divide by negative 1. And what happens anytime you divide an inequality by a negative? Then you have to flip that symbol. So now we have x is greater than or equal to 3. That's one possibility.
That's the question that I was asking.
What? Oh, yeah, sorry. Because that's a negative, you'll have to flip the symbol later on. Yes, ma'am.
I figured that. I was like,
Okay, sorry I misunderstood your
okay.
question. I thought you were just asking, should you change that minus to a plus?
oh, yeah, sorry. I should have.
Okay, well, that's okay. Now we
And
understand.
I figured that we were just like.
Yes, you're correct. Okay, so now same thing here. We subtract off the 2. Now we have negative 1x is greater than or equal to negative 1. We divide off the negative 1. And again, we have to flip the symbol. So now x is less than or equal to 1. Now, just like with the last problem, we're not done yet. We have to write that down on a number line and get our interval. So on a number line, we want x to be less than or equal to 1. And we want x to be greater than or equal to 3. That's what we're saying. And so what interval is that? Negative infinity, positive infinity. So long as x is somewhere between negative infinity to 1, union 3 to infinity. And now again, this is enough to hurt the brain. You really have to slow down in terms of what you're saying. So long as I choose x from this interval, then 2 minus x will land in this interval. And that's what I want. So you're choosing an x from this interval, and that will guarantee that 2 minus x lands in this interval, which means that the absolute value of x minus 4 is greater than or equal to 3. Yep. Where's that from?
It's basically it used to be called the
It's not on campus.
No, it's off of I don't remember when it's on the building that I go to is off of north of Oak.
What is it?
What is it? Like what it's a smoothie? It's like they call it like a buzz.
Oh, it's a smoothie.
Yeah. But it's like peanut butter.
Oh my goodness.
Bananas and coffee.
Are the rest of you wondering why Gabe didn't bring us one?
Right.
I'm wondering. That's distracting.
Yeah. They make them without beer.
Oh, wow, that's cool. All right, folks. Who has a question about solving absolute value inequalities? That's 2. We're going to do another couple.
How will you do graph?
You what?
I will some problem on what the graph.
Now that's certainly true. That would be a graph transformation problem. where you're taking an absolute value graph, which is a V, and moving it right, left, up, down, flip it upside down, all that. So if you tell me what number from the homework, I'd be happy to go over that. Well, find it during break, and then we can look at it. Yeah, I'd be very happy to. Okay, so we have two more problems here, which are pretty interesting. This first one, number 3, I'll go ahead and tell you is a trick question.
One concept I have from this is that you could subtract the zero or those answers.
Can we do this during break? Okay.
I'm sorry.
No, it's okay. I just want to keep it the flow, and then I do want to answer your question. We'll just do it during break. Okay, so again, what do we have to do first? Isolate the root, so we move the 2 over. And so we have the absolute value of 3x minus 5. And so now what do we say? This thing's distance from 0, it's less than -1 units away from 0. How can my distance from something be negative? Distance is always a positive quantity. So this is just nonsense. It's just nonsense. So this is no solution. Your distance from 0 has to be 0 or a positive number. There's no way that your distance from 0 can be negative, because distance cannot be negative. Just to show what this problem looks like so you can appreciate it, here comes Desmos. And within Desmos here we have absolute value of 3x plus 5. And then it's actually plus 1 if I move everything to the left. This is the graph. So where are the x-intercepts? There are no x-intercepts. So this problem has no x-intercepts, which is why it has no solutions. So remember, this is a big theme in the class. Any equation you can solve algebraically, you can graph it and just look at the x-intercepts. And since this thing has no x-intercepts, the problem has no solutions. And that's because distance can't be negative. Valeria, is that okay?
So you know it's not a solution because it's minus.
Right.
You have to start solving it to resolve.
Yeah, you have to isolate the root first. Yeah, you have to
So
isolate
answer
it.
is a solution.
Yeah. You always have to isolate the root before you can do any analysis at all. Yeah. Okay. Now, last one, folks. Actually, you know what? We can just cross out number 4. It's an interesting problem to be sure, but we're not going to be dealing with it. Okay. So those were absolute value inequalities. Now quadratic inequalities. Quadratic inequalities are really fun. These are really interesting problems. To talk about it, we first need to clarify some understanding of the first 2 lines there. So quadratic inequalities. It starts by saying when we ask f of x is less than 0, we want to know when the graph is what. And when we ask f of x is greater than 0, we want to know when the graph is what. So let's look at these 3 possibilities. Actually, 3 possibilities. F of x equals 0, f of x less than 0, and f of x is greater than 0. So first of all, everybody, we've already talked a lot about a function and the 2 possibilities that the y-intercept is equal to f of 0, and the x-intercept is f of x equals 0. So first of all, what does f of x equals 0 mean? Where are you? You're at the x-intercept. So if I ask the question, when is f of x equal to 0, you would say, when it's an x-intercept. Or you would say, when you're on the x-axis. Right? And just to take this a step further, let's think very carefully here. Whenever you think about any coordinate in space, okay, this is just some random coordinate, x comma y. When you have x comma y, and then you think about a function, then what you're really doing is input, output. Right? So you have your x-axis, which is your input number, your y-axis, which is your output number. And when you talk about a function, okay, like let's just say a simple function like f of x equals 3x, then the input is x and the output is 3x. So in general then, like, well, that's all I'm going to say is that f of x is equal to the output. F of x is equal to y. So another way of saying y is to just say f of x. Right? F of x is the actual output. F of x is the y value of the function. So that's something I'd like you all to memorize, that these 3 ways of writing a coordinate are all equivalent. And most importantly, f of x is equal to y. You've probably seen that already. F of x is equal to y. literally the y value of a coordinate is equal to f of x. So when we say f of x is equal to 0, what are we saying is equal to 0? 1. And indeed, let's just look at this coordinate. Maybe that coordinate is 8, 0. What do you know about the y coordinate? It's equal to 0. So we're literally saying f of x equals 0 means that the y value is 0, meaning the y value is equal to 0. Okay, so when we say, what does f of x equals 0 mean? It means that you're talking about a coordinate where? On the x-axis. Okay, so then what does f of x less than 0 mean? And keep in mind that f of x is y. What do we mean that y is less than 0? First of all, give me a number that's less than 0. -1. So that means that the coordinate that we're looking at is some value x, and what's the y value? Something negative. So what does that even look like on the graph? I'm just going to use a parabola here. Which part of my parabola has y values that are negative? Like this coordinate is something like -1, 8. That y value is positive. This coordinate is like 1, 3. That y value is positive. This coordinate is 2, 0. That y value is 0. This coordinate is something like 3, -4. So where's my y value negative? Exactly right, below the x-axis. When we say f of x is less than 0, we're talking about that part of the graph is below the x-axis. So when the graph is below the x-axis. So notice what we've said so far. F of x equals 0 is when the graph is on the x-axis. F of x less than 0 is when the graph is below the x-axis. So I think you can all take a guess. What does f of x greater than 0 mean? Yes, whenever the graph is above the x-axis. And again, if f of x is y, which is the y value, what's the potential coordinate right here? That'd be like the coordinate 2, 6. What's the value of the y coordinate? Positive. So when the graph is above the x-axis. Okay, so this was just my little demonstration. That would make sense. Now go back and write in your notes. When we ask f of x is less than 0, we want to know when the graph is below the x-axis. When we ask when f of x is greater than 0, we want to know when the graph is above. So when we do quadratic inequalities, which is what all the next few problems are, we're really just going to look at the graph of the parabola and say, when is it above and when is it below? And that's it. So for instance, number 7, I'm going to start us off by allowing us to quote-unquote cheat, and I'm just going to graph it for us. X squared plus 2x minus 3 greater than or equal to 0. So what are we asking? When is the graph above or on? Above or on. Exactly right. So if I write down now x squared plus 2x minus 3, there we go. When is the graph above or on? So everybody, let's draw a picture. You have your graph. The x-intercepts are at -3 and 1. So just make a quick sketch. Make a quick sketch, -3, 1. And the parabola, if we go back and look, this is a parabola. It's positive. It's facing up. So we have a parabola. Looks like this. And we'd like to know, when is the parabola above the x-axis? Even write the word above. So when is the parabola above the x-axis? Well, this tail over here, and this tail over here, as well as the x-intercepts, right? So now how do we express our answer? We express our answer in interval notation. So for when I say when is the graph above, I mean for what x values is the graph above. So for which x values is it above? 1 or more. Yeah, exactly. So there's infinity. So that's going to be bracket 1 to infinity. Or yeah, to the left of -3, which would be negative infinity. That's it. That's the answer. The answer is, when is this parabola above or on the x-axis? This interval right here. If you choose any x value from this interval, the parabola will be above the x-axis or on the x-axis. Yes, Omar?
In this case, we just like boil it, like break it up, factor it.
Okay, so good question. I just quote unquote cheated and we just looked at the graph. Now, is it really cheating? No. Because you're allowed to use your graphing calculator, you can graph anything you want. So you just look at the x-intercepts and boom, you know the answer. But to Omar's point, you could do this without a graphing calculator, no problem. Because you just take this and factor it. This is basic factoring. There's a 1 on it. What multiplies to make 3 that adds to make 2? So 3 is 1 times 3. It's got to be a negative 3, which means a plus times a minus. So which one's plus and which one's minus? Now plus 3 and minus 1. So I can immediately factor this into x minus 1, x plus 3. And therefore, what are the x-intercepts? If I set those both equal to 0 by the zero product rule, yeah, the signs change, exactly right. And we get 1 and negative 3. 1 and negative 3. Exactly what we thought. And then from this method, again, you would make a quick sketch. You just say, hey, I know that the x-intercepts are there and there. It's a positive parabola. It's facing up. And away you go on the exact same solution. So do you need a graphing calculator to do this? No. You can just factor it. So that was number 7.
For the test, do you want us to show the work?
Well, I always want you to show work.
Okay, so then-
I would show as much work as possible, but the minimum amount of work you need to show me is a graph.
Oh.
Show me a graph and shade in heavily the part that you're talking about and write the word above. Because it's not just me you're trying to convince, it's your whole audience. You're trying to convince somebody who's reading your work to know why you just said the answer was what it was. So, number 8. What question are we asking now? Just looking at the symbol. We're asking, when is the parabola? Well, to be fair, we need to move all the terms to the left first. Let's go ahead and move all the terms to the left first. Sorry, we should really have done that first. So we have 3x squared less than or equal to 11x plus 4. We'll move all the terms, so minus 11x minus 4. So now we have 3x squared minus 11x minus 4. Yeah, so I'm sorry. Remember, we only know how to interpret function is less than 0 or function is greater than 0. So you do have to have it set equal to 0 first. Okay, so then Hector, back to you. We're saying when is the parabola less than or equal to 0? So we're asking when is the graph? Less than or equal to 0, which means where would it be? Below or above? Below. Yeah, we're looking for when is the graph below. And just think, less than, is down, and greater than would be up. So we're asking,
If it has the equal
then it's on. So this means below
on,
or on. Yeah, very good. Below or on. So when is the parabola below or on the x-axis? And again, at this point, you can just graph it, find out the answer. This particular problem, is this basic factoring? No. And can we divide out of 3? No. So that means that we have that long process to do, where we have to rewrite the middle term and then factor by grouping. It just takes a couple extra minutes. You could also graph it, so long as you show me a graph. Yeah, so let's walk through this. This is a good review. Everyone, if you wanted to factor this, you would say, I want to rewrite this term right here. And to do that, I need to multiply a times c. So 3 times negative 4 is negative 12. And I do a factor table for negative 12, and I ask which of those adds up to negative 11. So 1 and 12, 2 and 6, 3 and 4. I'm multiplying to make a negative, which means 1 has to be positive and 1 has to be negative. And I need them to add up to negative 11. So which pair of numbers? Yeah, 1 and 12. Which is positive, which is negative? Yeah, positive 1 and negative 12. And now you can check your work. Is 1 times negative 12 equal to negative 12? Yes. Is 1 plus negative 12 equal to negative 11? Yes. So now that's how we rewrite our middle term. Now, I'm not going to write plus 1x minus 12x. I'm going to write minus 12x plus 1x, because you can choose which order to write it down. All we need is to rewrite negative 11x. I'm going to write it as 3x squared minus 12x plus 1x minus 4. Yeah, that way I don't have a negative sign right there. My life is a lot easier if that term is positive. So now we do grouping. We factor we group the first two, group the second two. From here, I can factor out a 3x. So that's x minus 4. From here, I can factor out a 1. I mean, you really can't factor out anything. But the key is that they're both x minus 4. And therefore, one of them is x minus 4, and the other one is? Yeah, 3x plus 1, the big's left-hand side. Now, everything that we just did was to find the x-intercepts. I'm suddenly switching to equals 0. If the problem is actually less than or equal to 0, but I want to find the x-intercepts. And in order to find x-intercepts, you're asking when is f of x equal to 0, because you need to use the zero product rule, something times something equals 0. So now I said both of these equal to 0. We say x minus 4 is equal to 0, 3x plus 1 is equal to 0, and therefore x is equal to 4, or 3x equals negative 1, divided by 3, x is equal to negative 30. Well, now, that sure was a lot of work. And we could have just graphed it to begin with. But that was a nice review using factoring by grouping. So where does that leave us? We wanted to ask, when is this parabola below the x-axis? We can now make a picture. We make our picture, our x-intercept is at 1, 2, 3, 4. And at negative a third, which negative a third, I'm just going to put a little dot there between 0 and negative 1. I'm going to call that negative a third. And then there's my parabola. Now, what were we asking again? Where's the parabola below? So I shade that in real nice. You just shade it in with your pencil. And I'm talking about the x-intercepts because it's less than, it's below or on. And this is a simple interval. It's just between negative a third and 4. So your answer is bracket negative a third and 4. Again, during the test, if you have any questions at all, you can come ask me. I might not answer your question, but sometimes asking the question, you realize it as you say it. You're like, how do you do that? Oh, right? But if you have a question about your calculator, I'll show you how to use your calculator. I'll show you how to graph this on your calculator. I have no problem doing that for you because I'll be teaching you as you do it. So, okay, I would like to finish these. Oh, well, no, we can just take a break. That's a good stopping point. We have this idea. Let it marinate. That's 132. Let's come back at 142. Hector, if you can find that problem that you wanted to show me.
I will ask Lee after class is over.
Hey, you can do. Oh, okay. You're gonna go to the snack. That's fine. You can ask me though, Hector.
I had a headache because my stomach was hurting.
You what?
I had a headache right now because I was
Ah, that's the worst. I wrote it on the board. 142.
See, I wonder how fast the bacteria is really stay.
We shall see. You better run. Not that fast. Nadine, you got a question? Valeria, got a question?
No.
Emily.
No, I'm just looking at the No, I actually like that. I feel so lame. I use this called brain over time. And I want to buy me more fruit. I want to like this. Yeah.
I was looking at this. Like last year, no, last year this was just makeup. This.
Oh, okay.
This one, this one. And then this year is this one. And this one. question. The office hours, such as going.
You just go to my office. You just go up, I look at your notes, and then you're done.
Okay, cool.
Yeah.
Okay. Awesome. Thank you.
Have you been up there yet?
No, I've been there before class, remember? But I went to, so you can wait.
Yeah. Then that's all. You just have to go once. Have you been up there once? You've been to my office.
Yes.
Then you're good. You don't have to go up again.
Okay.
Yeah, it's just
cool.
once.
Okay.
Okay.
No. Like before this semester. That's funny. I think so I had to go to his campus, so he needed to.
I don't remember that time.
I don't know. Anyways,
I went right away because I forget, I tend to forget everything.
I'm going to. So I stay here, I only have
Oh, I haven't been talking in a while, and whenever I drink, it hurts. I get sugary. I'm like, all hyper. I remember, when I was thinking about 160. I drink coffee before the test, and it was not good. I couldn't concentrate. I was like, oh my god, I don't remember anything. I was panicked.
So,
Oh no, my brain was not loud.
because usually you were supposed to be FaceTiming and it's not like to study, and then he was like, oh, I'm not really doing this. It's gonna be fine. I was like, oh, I'm just kidding.
Oh yeah, I asked you something and you were, I was cleaning my house and I'm kidding. I'm like, you were kidding because it was quiet. No, it was the house is messy. This is like whenever there's like 7 people in total. So like in my bed, everyone eats at the same time, so like everyone's dressed. So like whatever. And then we come back
And everybody has stores.
no.
It's
Okay,
your-
so my brother is lonely, but like my mom comes from work and what I do is like I try to help her out. It's a very good because she likes it. So she likes listening to music and her voice and stuff. So I'm like, yeah, my sister is doing.
My sister.
Oh, I have He's 15. He's a he went to a little phase or stage where like back and he went and I'm like, oh my god, but hard to. Yeah, that's what we're doing. This is 3 weeks. Me and I don't really have to supposed to go.
And I put this one down. Dang, that's why you should have food other than this. So you do that. Like this.
My love no, it's over 4 years. He's 20, he's about 24 now. You look the same. He's not older than
Yeah, I was just wondering.
no. Oh, you won't.
Yeah, right. That was good.
He's been here long.
Oh, no, because I think one of the things we used together.
No, but yeah, because it was there when he was in high school and now we're. Yeah, because when he started college, I was learning a freshman, like a sophomore in high school, and then now we're here. He used to be embarrassed. Really? Yeah, he's annoying. No, he's nicer now, but when I was younger, he was.
Maybe he was like,
No, he was annoying. I was never annoying. I just kidding. It's because he doesn't like taking it sometimes. Yeah. He's like, oh, you're always walking. It's because I'm the oldest one, basically. He's, just kidding. You know how it is? Like, you're the female, and you're the middle child, and I
well, I'm here with this child.
at least you're not the middle. Oh my god. It's like, see, I'm the oldest. I'm the oldest daughter. My mom expects me to like do everything basically, and my brother, he's lazy.
Sometimes I feel that I'm the one who's that way. That's I love you. So, like, sometimes when you
I know.
actually, that's
Actually, you made it back. Hey, it's 1:42. Let's do it, folks. All right, very exciting. These next couple of questions are so fun. They are so fun. They are so great because it demonstrates how conceptual understanding of a problem can make the problem incredibly simple and easy to do. So, let's take a look at number 9. We have x squared plus 9 is less than 6x. Now, first of all, what do we have to do? Move everything to the left, so we subtract 6x from both sides, and now we have x squared minus 6x plus 9 is less than 0. What are we asking about the graph? When is the graph?
Less than or equal to 0.
Which means below. We want to know when is this graph below the axis? All right, what x values can I plug in to make this parabola have a negative y value? So we go ahead and factor. We can do that. So what multiplies to make 9? It adds to make 6. So we're going to factor the 9. That's either 1 times 9 or 3 times 3. We're multiplying to make a positive 9, so that's either plus times plus or minus times minus. Yeah, we want it to add to make a negative 6, so it has to be minus minus. And so our answer is x minus 3 times x minus 3. And we're going to find the x-intercepts first. So we change that to equal 0 because we want to use the 0 product rule to say, hey, what are the x-intercepts? And if we solve both of those equal to 0, x minus 3 equals 0, x minus 3 equals 0. And my goodness, what does that mean? It means x equals 3 and x equals 3. There's only one solution. And if we draw our graph now, where's our x-intercept? Just 3. What does that mean about our parabola?
That's where it's only on it.
Yeah, it's only on it. Right? That's one of our possibilities. There's only one solution. Even though we list it twice, x equals 3, x equals 3, there's only one x-intercept, which means the parabola is resting on the x-intercept. So where is it below the x-axis? It's not.
It's not.
So the answer is no solution. There is no value for x that you can plug into this quadratic that would produce a negative number. No matter what you plug in, this value is going to be, well, 0 or positive. And just for fun, to try value, I'll plug in 1. If I plug in 1, 1 squared is 1, minus 6 times 1 is 6, plus 9. 1 minus 6 is negative 5, plus 9 is 4, that's positive, not negative. So that's an interesting problem. There is no value of x. So when is x squared plus 9 less than 6x? It's not. It never will be. That's very interesting. Okay, one more interesting one, number 10. We're asking, when is 9x squared plus 16 going to be greater than 24x? So when will that be true? What do we have to do? Move everything to the left, so 9x squared minus 24x plus 16 is greater than or equal to 0. So we're asking, when is this graph on or above? Yeah, on or above. So we would say on or above. Greater than means on or above. So once again, we factor. Now, we go through the process, you factor. Can we factor? So first of all, this is not basic factoring, there's a 9. Can I factor anything out? No. Because nothing goes into 9, 24, and 16. Therefore, we'd have to do that really long process where you multiply 9 times the 16, which would turn out to be 144, and then you'd have to sit there and do the factor table for 144, yada, 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 and then you'd have to rewrite the middle term, and then you'd factor it by grouping. And at this point, you're probably all saying, let's just, no, let's just graph it, right? I'm not saying that it's not worth your time to factor by grouping. It's fine, but we have another solution at our disposal, 9x squared minus 24x plus 16. Plus, this is going to be so satisfying visually. Remember, what question are we asking? When is the parabola on or above? Well, that's just when it's on. We're asking greater than or equal to. So when is the parabola on or above the axis? Always. Exactly right, always. So that means what x value can I plug in to make this thing greater than or equal to 0?
And that's 1 right now.
Yeah, because when is the parabola above the x-axis?
Oh, sure.
The whole thing is. Yeah, the whole thing is. So the answer is any x value. Always. The answer is always. When is it on or above? Always. What x value can I plug in? Any x value. What's that interval? Sure, you can plug in 0. That'd be 0 plus 16 is greater than 24 times 0 is 0. Is 16 greater than 0? Choose any number at all. Plug it in, and the left side will be greater than the right side. That's good. Okay, well, that's the problem. Notice there was not a lot of math we had to do. Well, that's not fair.
I was just going to say, so if you were to do it the other way.
Factor by grouping?
Yeah.
Yeah, you'd have to come up with which pair of factors will actually give you the difference of 24. I mean, 1 and 144, 2 and 72. It's not going to take that long. 3 and
48.
hey, way to go, 48, and then
6.
4 and what?
36.
Yeah, 36.
6 and 24.
Oh, you already have all this.
I was trying to.
Oh, you did it. Okay, great. So
That's all I
6,
got.
7,
That's all I got.
8, and 18, and then 9 and 16. And I think we might already have it because we want to multiply to make a positive, but that means plus times plus or minus times minus. We have to add to a negative 24, so it's got to be minus minus. So it's 12 times 12 times 12. Okay, so it's all the way further down on the list. Yeah, negative 12, negative 12. So if you did that, and you wanted to have a lot of fun in your life, and you wanted to finish factoring negative 12x plus negative 12x plus 16, you would factor by grouping, and then you'd have 3x out of 3x minus 4, and then you'd have negative 4 outside of 3x minus 4, and fortunately they're both 3x minus 4, and you'd have 3x minus 4, and 3x minus 4. So what do you know, it's the same thing twice. So, hey, it's the same thing twice. That makes sense. Because x is going to be equal to 4/3, which is 1.333, and that was indeed the one solution we had was at 1.33333, and it was the same solution twice, which is why I'm sitting on the axis. So, yeah, who said that, Gabe? Yes, you totally finished it that way. Omar.
If it was just greater than, would we exclude the?
Yeah, you would. Great question, Omar. If this had said, when is it strictly above, then you'd have had to say, everywhere except 1 1/3. Right? You'd have to exclude that point. You say, well, yeah. Yeah, so if you plugged in 4/3, right, wait, negative? No, positive. Yeah, if you plugged 4/3 in, this thing would actually be equal to 0. So that'd be false. So you'd have to do the interval, what, 4/3? With an open circle, shade to the right, shade to the left. So negative infinity, 4/3, and then 4/3 to infinity. Yeah. Very good, folks. Folks, I just want you to know, I'm really trying to make sure that we understand the concepts behind what we do and not just do rules. And math is just so much more interesting that way, and I just hope that you're experiencing that. Because really that's one of my biggest goals, is that you're constantly getting the answer, why? And the definitions that we're receiving are allowing us to answer the question, why? Okey-doke. So I believe we just have a couple word problems here. We will do them, and then we will do regression, which is a lot of fun. Okay. So let's look at number 11. The profit in dollars made by selling X bottles of tonic. What is tonic? Yeah, a potion. Is that like the old medicine snake charmer potion that you'd sell and make people better? Either that or tonic water, which is just a foul-tasting carbonated beverage. So the profit is there. So there's our profit, number 11. The profit is negative x squared plus 25x minus 100. So that's our profit. And they're saying that is only valid between 0 and 35. So for whatever reason, we're going to assume that you only have 35 bottles of tonic and you're willing to sell some of them. So you were in your grandma's attic and you found 35 bottles of tonic and you're like, I'm going to sell some, I'm going to keep some, whatever. So how many bottles of tonic must be sold to make at least $50 in profit? So first, I want to show you the visual answer to that question. We want to make at least $50 in profit. So let's look at this graph, which is negative x squared plus 25x minus 100. And there's the parabola. But I want only to consider more than 50. So I make the horizontal line y equals 50. And when is the profit more than 50? You all see it? Yeah. It's this little bloopy-doop right up here. So from where to where? How many bottles of tonic? Yeah, between 10 and 15. So that's it. That's the answer. We're already done. That's the answer. It says how many bottles of tonic must be sold? Between 10 and 15. So you would just go ahead and write down between 10 and 15. Isn't graphing wonderful? Yes, Mr. Yes. Oh, that's what I thought. So we would say the answer is between 10 and 15, but really on an interval, how would we express that? We don't say things like between 10 and 15. We say bracket 10, 15 bracket, because we're sophisticated. Okay, now what we just did was solving the problem visually, graphically. We need to also know how to solve it by hand. So what are we saying about profit? We want it to be at least $50. So what are we saying about our profit? We want it to be what compared to 50? Yeah, we want that. So what that means is now we've set our whole equation, negative x squared plus 25x minus 100. We set that whole thing greater than or equal to 50. That's what we're saying. Right? We're saying we want our profit equation to be greater than or equal to 50. And we'd like to know what values of x can I plug into that function such that the value of that whole thing would be greater than or equal to 50. So what do?
I move the 50 over to 0.
Yeah, move the 50 over so that we can ask our basic question, when is negative x squared plus 25x minus 150 what compared to the x-axis?
Greater to 0.
Which means it's above. We want above or on, right? So we want the graph to be above or on the axis. So we factor, and notice we have a leading negative. I would like to get rid of that leading negative. So how do we get rid of a leading negative? I like that. We can just multiply the whole darn equation by -1. Or you could factor out a -1 and then divide it off. I think multiplying the whole darn thing by -1 is a little more effective. Now, when we multiply an inequality by a negative, what do we have to do? You have to flip the sign. So first, make sure you change all the signs correctly. All the negatives become positive, positive becomes negative. But I just multiplied by a -1, so I flip the inequality. So now what are we asking? When is this parabola below or on? Boy, like, you really got to follow the ball on this. Like, what are we asking at every step along the way? So now this we can factor. What do we multiply to make 150? We can make our factor table: 1 and 150, 2 and 75, 3 and 50, 4 and nothing, 5 and 30, 4 and nothing, 6 and 25, 7 nothing, 8 nothing, 9 nothing, 10 and 15. So what adds to make 25? Remember, this is a positive 150. That means a plus times a plus or a minus times a minus. Since we want to add to a negative, it has to be minus and a minus. So what adds up to -25? Yeah, 10 and 15. So we're done. That's really x minus 10, x minus 15. And so we use the zero product rule to find those x-intercepts. And we say either, and by the way, maybe you all know now that you can just change the signs on the numbers. Right? So either x is 10 or x is 15. You know what we got, which is what we got, right? We now know that our x-intercepts are 10 and 15. We also know this parabola is facing up, so your graph will look like this. And our question is, when is this parabola below? And when is it below? Between 10 and 15. The exact same solution that we arrived at. Which method took more work? Well, I'll go this way. But it's important that you understand how that process works. After all, you won't always have a graphing calculator nearby. You could crash on a desert island and have to save humanity. And you'll have to do all this by hand for a while.
So once again, in the test, we can do the graph. We can graph it, and then we just
Well,
graph and
see, here's the thing. I hear your question. If you do this way, you would have to make sure to show me that you had that upside down parabola, you graph the line at 50, and then you show me these points such that that's at 10 and this is at 50. I mean, you'd have to give me one complete graph to know, to convince me that you really saw those points. Yeah.
What I'm seeing. Okay.
Yeah. But on the other hand, if you just go ahead and set it greater than or equal to 50, then factor, I mean, these are really the skills that we're working on in chapter 2. This is really what I'd like to see. What I'd really like to see you do is you can check your work, but this is really how you would show your work. Yeah. Okay, let's try another one. Number 12, we talked about cost. So first of all, what do we always hope about cost? Do we want to maximize cost or minimize cost? We want to minimize cost, which would imply any cost function is probably going to be a parabola facing up because you want to find the minimum value of cost. So just kind of spitballing here, approximating, they're giving us a cost function, which is a parabola and it's facing up, and that makes a lot of sense because you want to minimize your cost. So now they're saying that's our cost function. Find the number of pens which can be produced for no more than $1,100. So we have our cost function. It's equal to x squared minus 10x plus 27. And this value, once you compute it, is our cost. So what are we saying about the cost compared to $1,100? We want the cost to be no more. So not more than, less than. Right? Now, is it less than or less than or equal to? Yeah, less than or equal to. Yeah, we just don't want the cost to be more than 1,100. We're fine with the cost being 1,100, but ideally we want the cost to be less than 1,100. Now, so far is what I wrote down correct. If we move that 1,100 over, we're going to have x squared minus 10x minus 1073 is less than or equal to 0. What multiplies to make 1,073 that adds up to 10? I don't know that anything multiplies to 1,073. We do have one thing we have to fix. What did it say our units are? It says the cost is in hundreds of dollars.
Oh, so we have to just make just 11.
Yeah, it's just 11. That's tricky, right? They're just being tricky. So what we're really saying is we want the cost to be less than or equal to 11, which represents $1,100. Now when we move the 11 over, that's a whole lot more reasonable. We have x squared minus 10x plus 16 is less than or equal to 0. So we're talking about a parabola, And we're interested in where that parabola is what compared to the x-axis?
Below or on?
Yeah, below or on. So less than or equal to means below or on. So I'm going to write below or on. And away we go, factoring, using our favorite math F word. Factor.
It'd be 2 and 8.
Yeah, probably 2 and 8. Let's look. 16 is 1 and 16, 2 and 8, 3, 4 and 4. And we want it to be a plus times a plus or a minus times a minus. And we want it to add up to a minus, so it has to be both minus. So yeah, it's negative 2 and negative 8. So we say x minus 2, x minus 8, which change the signs, and our x-intercepts are at 2 and 8. Now we draw a graph. We say, well, our x-intercept is at 2, 3, 4, 5, 6, 7, 8. We have a parabola. And we wanted to know when the parabola was below the x-axis. And so it is below the x-axis, between 2 and 8. So that means our interval would be 2, 8. Now, I want you all to know that if you write down the answer, bracket 2, 8 bracket, that is absolutely the accurate answer. But it is also the answer that you would only give to an enemy, to someone that you dislike and don't care for. Because what did the question ask? Find the number of pens that can be produced. So how many pens can be produced between 2 and 8? It says to produce X thousand pens. So what do these really represent? 2008. So if you were talking to a friend, you would say between 2,000 and 8,000 pens. That's if you were talking to someone you cared about, right? But if you just wanted the accurate answer, well, yeah, the interval 2 to 8 is correct. That's correct in the context of this problem. But if you're talking to a friend, you would tell them what's what. You wouldn't be like, here, take the 2 to 8, deal with it, and like make them go interpret the problem, right? That'd be terrible. So again, word problems, the answer is in words, and that's a nice little tidbit there. The words you use to answer word problems should be to a friend, right? You're trying to be friendly, you're trying to be nice, you're trying to be helpful. Okay, super duper. This last one, we'll just kind of look at it real quick. I'm not going to finish the whole problem. Ooh, I forget, this might be a good one. So this last one, we're talking about the height of a model rocket above the ground. And they're telling us that the height is given by this function, h of t equals negative 5 t squared plus 100t. And it says, when is the rocket at least 250 feet off the ground? So what do we want to say about this height compared to 250? Yeah, when is it at least 250 feet off the ground? So when is it greater than or equal to 250 feet off the ground? Now, I want to show you this one. We didn't even graph the cost function one. But the rocket one, see, this is really interesting. We have a function to express the height of our rocket, which is negative 5x squared plus 100x. So there's the height of my rocket. Let me get a better window. Windows are so meaningful. When you have a bad window,
280 what units?
between 2 and 8,000 pens. Wait, is that what you just said?
No, I'm asking what units are.
Oh, you tell me. The problem says the height h in feet.
That was miles. You didn't ask.
Oh, yeah, you certainly would be. Okay, so here's our rocket. So is everyone clear? This is the path of a rocket. What's the highest the rocket gets? 500. What are we wondering? When is it at least 250? So when is it at least 250? Yeah, between 2.9 and 17 seconds. So roughly between 3 and 17 seconds, it's at least 250 feet in the sky. Now, okay, so we all see that graph. This is the actual graph of what's actually happening, and we want to find those 2 points. Now, of course, with Desmos, you just do it, or with your graphic calculator, you just do it. But now let's take a look at how this problem is done by hand. So we're saying we want this to be true. We want the height to be more than or equal to 250. So what do we do? We bring that 250 over because we always want every function to be set equal to 0. Why do we set every function equal to 0? Exactly right, because that's one of our fundamental questions in this class is, you set the function equal to 0 and set it equal to 0 because that's the x-intercept. We're always interested in the x-intercept. So we have this. What's the first thing we want to do? Factor out the 5 and take out the leading negative. Exactly right. So taking out the 5, we could go ahead and do it this way. You can divide every single term by -5 all the way across. That's a valid way to do algebra. You can just divide both sides by -5. I like this way because now I can clearly see what my answers will be. So those cancel out. I have t squared. 100 divided by 5 is -20. And then negative over negative is positive. That's 50. And then I divided by a negative, so I have to flip my symbol. So you'll notice that I went from asking, when is this parabola above the x-axis? Now I'm asking, when is this parabola below the x-axis? And what's remarkable is that it's still going to give me the same answer that we want, which is between 2.9 and 17. Okay, so now we have there. Now, as always, our first thought is to factor. So we say, what do we multiply to get 50 that adds to make -20? So this is a positive 50, so plus times plus or minus times minus, but it is a minus, so it's going to be both negative. That's 1 times 50, that's 2 times 25, that's 3 times nothing, 4 times nothing, 5 times 10, and that's it. So if I put a negative in front of those, which one adds up to -20? None of them. And so, Omar, if you can't find a way to factor it, what does it mean? You have to use the quadratic formula. Yeah, that just means it's not factorable. There are still x-intercepts. You know, we don't know what they are yet. It could be 2, 1, or 0. We don't know. All we know is that we don't know. We know that it can't be factored. So we give up on the factoring idea, and we go back to the quadratic formula. So we say, all right, A is 1, B is -20, C is 50, and away we go using the quadratic formula. So the x-intercepts are equal to -b plus minus square root of b squared minus 4ac all over 2a. So -20, a, c, a.
I feel like it's going to be like -70 or just -7 and 5. Like 5, yeah.
Feel like it is.
I don't know.
So we're going to do it. All right, so 20 plus or minus, then inside we have 20 squared is 400 minus 200 all over 2. Yeah. So now we have 20 plus or minus root 200 all over 2. And this is a great problem to do. Right here, we would say to ourselves, okay, we finished the quadratic formula, but now we have to simplify. Because root 200, is that divisible by a square number? What? It is. Which square number? Now, to be fair, you know, to build experience, you would sit there and you'd write out all the square numbers. You say, oh, okay, here's all my square numbers. And you're, you know, either copying it off of a list or you're doing it in your head. 11 squared is 121. 12 squared is 144. 13 squared is 169. 14 squared is 196. So that would be where the 200 is. And then you start working to the left, dividing until you hit 100. 100 goes into 200. So then we'd say, okay, root 200 is really root 100 times 2, which is really root 100 times root 2, which is really 10 root 2. And then we would go back. You don't have to write any of this down. Then you'd have 20 plus or minus 10 root 2. And then from the top, we could factor out a 1 and 2. Okay. 10. You can factor the 10 out of 20 and 10. So I bring out a 10, and that would be 2 plus or minus 1 root 2. And then I have a 2 down below, and then what can I do? 2 goes into both, so then 2 goes into 5 times, so it goes out once. And that means we're down to just 5, 2 plus or minus root 2. Okay, so we get all the way to there. And in the context of this problem, none of this matters. We didn't have to do any of that. Because we're asking an actual problem. And how do we answer word problems? In words. And who are we giving our answer to? A friend, not an enemy. You would never walk up to a friend and say, hey, when is the rocket overturned off the ground? And you're like, oh, you know, between 5 times 2 plus or minus root 2 seconds. Like, who's going to know how many seconds is that? You're like, is that 5 seconds? Is it 6 seconds? I mean, how many seconds is that? So no, we're talking to a friend. 2.5 seconds. Right, yeah, who knows? So instead what you'd say is, I'm going to get a decimal approximation. So 20 plus or minus, what is the square root of 200? So you do the square root of 200, and you use a lot of decimals because Desmos wants at least 4 decimals. So 14.1421 all over 2. And then you break that into 2 alternate realities. And you'd say 20 plus 14.1421 over 2, or 20 minus 14.1421 over 2. And then you compute both of those. You're doing this for your dear friend who you love. And the first one turns out to be, my goodness, 17.0710. And the second one turns out to be 2.9219. So that'd be the correct rounding. Actually, the first one rounds to 1107. There. And are those the answers that we got from Desmos? There. So again, this is for a friend. This is for someone you care about and you like. You're not going to give them this wonky answer up here, especially because it's a word problem. You want to know how many seconds is it. So you would say t between 2.92, or really 2.93 maybe, and 17.07 seconds. But really, as an interval, you would say interval 2.9290, comma 17.07. Right. Now, of course, if you're really friends with somebody, you'd say between 3 and 17. But if you were really close friends, you know, if your families knew each other, or if you're like best friends, you'd be like, for a while. But then, you just lost all of your accuracy, right? All right. So there's our word problems. We now get to do a really cool and exciting segment here. What?
I don't know. Maybe this might not be fun for the rest of us.
No, I guarantee it. I guarantee this is going to be fun for everyone. You know, especially to the extent that you just had fun with all that stuff we just did. I guarantee this is going to be fun too. Plus, this is more calculator work than factoring work. There's no factoring at all. This should be a nice little break. This should feel good. This should be like, oh, great, you know, something more simple, straightforward, conceptual, no heavy lifting. And it's very interesting because we're talking about society. Really what I'm asking is, how does a city make decisions about how to prepare their city for future populations? So let's say that you were the governor of a town, and the population of your town is currently 1,000 people. So first of all, have you ever lived in a town with only 1,000 people? It's a pretty small town. Nice team. And so you're the governor, and you just received information that within 2 years, the population of your town would be 100,000. So I mean, can you really imagine it? You're living in this little sleepy town of 1,000 people, and within the next 2 years, your population is going to be 100,000 people. I mean, I don't know if it could happen or not, but what would you have to do? Well, that's one option. You know, you could start an education program to educate people about birth control, but probably within 2 years, 1,000 people can't give birth to, 99,000 people. So we're probably talking about immigration, people immigrating into your area. But do you even have enough homes for that many people? You need to do what? Build apartments, build houses. Do you even have enough water supply? You'd have to increase your water supply. Do you even have enough roads and freeways? You'd have to build more roads and freeways. Like, I'm really wondering, like, what if your town was going to go from 1,000 to 100,000 people? How much work would you have to do? Yeah, not to mention jobs, import, export, food, waste management, trash. Like, there's a lot of considerations. So as a city, or as a governor of a city, it's very, very interesting to you to know how your population is growing. Because if your population is growing radically, you would need to build a lot of infrastructure. If your town is not growing at all, you wouldn't have to do anything. Or maybe you want to do advertising and bring people to the town through new businesses. Or if the population of your town was shrinking, you could probably let go of certain resources. Like, geez, I guess we don't need that big of a freeway, and we don't need all these other things. We can cut back.
It's more for the
Yeah, well, we're assuming the governor is working in our best interest into saying what's right for the people, or what she said. So what we're going to do then is talk about regression. And the first thing I'd like to do is just show you, first of all, you can all go to this tool online. If you go online to just regression calculator. What I really like is the Desmos, there we go, linear regression calculator. So this calculator just comes up, and what it does is gives us an example of a scatter plot. So everybody here, you're all familiar with a scatter plot, right? A scatter plot just means you have some data. What kind of data do you have? Well, it could be anything you want it to be. So just for fun, I'm going to say that this data represents height and shoe size. So generally speaking, as people get taller, what happens to the size of their shoe? It gets bigger. You know, it's just a natural thing that if you're really tall, you probably have big feet. Is it impossible for a tall person to have little feet? It's not impossible. Is it possible for a short person to have huge feet? Sure. These things are all possible. But for the most part, you would expect your data to clump up along this line, right? That the taller you get, the bigger your feet get. You could have a weird data point, like a really, really tall person with short feet. You could have an outlier right here. If you had a point right here, that might look a little strange, like, hey, what's that point doing all the way over there? Or you could have a really, really short person with huge feet, and you could have an outlier up here. You're like, where did that person come from? But for the most part, humans are pretty, statistically the same. And if you have a tall person, you've got big shoe sizes, short person, small shoe sizes. So when we talk about things like humans or non-physical systems, what's that? Yeah, things grow in proportion, but data is messy. Data is always messy. You're just going to have a scatter plot, and what we want to do is draw. Well, you know what this line is called? It's the line of best fit. It's the line of best fit. So you take a bunch of data, which is messy because humans are different from each other, and you draw a line of best fit. And that line of best fit is like this pretend, like if I assume that humans behave like this line does, then I could just say, hey, somebody who's 8 feet tall is going to have that shoe size. I could say someone who's 6 feet tall is going to have that shoe size. Or someone 4 feet tall is going to have that shoe size. Now, obviously, is any human actually going to be right on that line? Maybe a few of them are. Most humans will be off the line. But generally speaking, what we say is this line of best fit is our pretend model of an ideal human, where if you use that model, whatever answer you predict, it might not be exact, but it's going to be close.
It has tolerance.
Yeah, exactly. There's an error tolerance. Exactly right. So what we're going to talk about right now is linear regression. Now, have you ever used this word regression?
Well, we regress or not progress.
Yeah, exactly. Regression is the opposite of progressing. So I've heard people talk about regression, like, oh, I'm regressing. I was doing such a good job of exercising every day, I totally haven't for like a week, I'm regressing. Or our daughter, she's 2.5 years old, she's a fairly good sleeper, but every once in a while she'll go through this like spell where she wakes up and cries in the middle of the night, and then my wife will be like, oh no, our daughter's regressing. Right? What?
The first time you said that word, the word is that drugs.
Regression. What does this have to do with drugs? Oh, like to someone who falls back
Yes.
into, is that what it's actually called? Regression, if you fall back into drug use?
Yeah.
Those word.
Why are you pointing at me about I just
No, we were just talking. I'm not
Okay.
pointing at you, but it's called something. And what's it called when you quit, but then you fall back into it? There is a word for that. Not rehabilitation. That's different.
No, that's when
Relapse.
Yeah.
Relapse. There we go. Okay. So, in any case, regression means the line of best fit. So when we talk about a linear regression, we're talking about calculating a line of best fit. Now, the calculations that go into a line of best fit are beyond what we have to do in this class. We don't have to do the calculation for line of best fit. Our calculator will do it for us. But I just want you to notice, as I move these data points around, this program is so cool because it automatically moves the line of best fit to recalculate itself automatically to go along with your points. So, like right now, I have a really tight fit. Right? We would say that that's a really good linear regression, or better yet, the data is very regular. Whereas if I just, had a bunch of really weird data points, well, in theory, there wouldn't be much to say about it. It's just a bunch of random data. So the next thing I want you to see is, well, first of all, we're able to calculate this thing called linear regression line of best fit, but also we have this idea of a correlation coefficient. Oops. Correlation coefficient. Where, here we go, I'm gonna make that bigger. That's kind of bigger. No, that's okay. There. So other than the idea of drawing a line of best fit, okay, so like here, that'd be a line of best fit, line of best fit, line of best fit, no, line of best fit, line of best fit, line of best fit. There's also the tightness of the data. How tight is the data to your line of best fit? And first of all, the way we measure this is on a scale of 1 to -1. So it's between +1 and -1. +1 implies positive slope and positive correlation. You say positive correlation, but it also means positive slope. -1 means negative correlation, and it also means negative slope. Now, 1 is perfect. That means your data is perfect. It actually follows the model exactly. Whether it's a positive or negative, 1 means your data is super tight, super good, 100% predictable. If your correlation coefficient is only like a 0.9, it means your data is pretty good. Your prediction is only going to be so good. You know, you're going to have a tolerance, an error tolerance. Whereas a 0.5 correlation coefficient is terrible. Your data is sloppy. Your prediction model is not going to be very good. You can still try to predict it, but you wouldn't expect your model to be excellent. A correlation coefficient of 0 means there is no model. There is no correlation. That would be like if you graphed shoe size with eye color. What does eye color have to do with shoe size? There's no prediction there. Okay, and so on. So this is called our correlation coefficient. So those are our two ideas. We can draw a line of best fit, and then we can talk about how tight the data matches that line of best fit. So does everyone have a graphing calculator? Because what we need now is to do a graphing calculator. I'm going to walk you all through the steps. It's, you know, like we're just going to walk very slowly through the steps. So everyone take out your graphing calculator. Valeria, you got here just in time. Everyone take out your graphing calculator. Who needs one? Emily, you have one? Oh, it's right there. You have one, you have one? Okay. Hector, you have one? Oh, yeah, you have it. Okay. Omar, I have no idea how to give you instructions, but maybe you already know how to do it? Oh, wonderful. Okay. Everyone at the TI, I'm about to tell you. So, here we go. First of all, let's just look at our problem and do a graph by hand. So, what we have here is the census data for Lake County, Ohio. Now, just look at the population in Lake County, Ohio, and tell me what's the population doing? It's increasing, right? So, okay. So now, we're just going to make a quick little graph by hand, because making a graph by hand is a valuable skill, especially to know that it doesn't have to be perfect. It just has to have the data. So I'm going to put my years on the time axis, the t-axis, the x-axis. I'm just going to start putting 1970 right there, then 1980, and then 1990, and then the year 2000. So you'll see, I didn't start at 0. I don't even know where you'd start at 0. Would you put 0 BC, the birth of Christ? I mean, when do you start your graph? I'm just going to start with 1970 right there. Okay? And then likewise for the population runs between 197,000 and 227,000. So I'm going to put 190,000, 200,000, 210,000, 220,000, and 230,000. So you'll notice I've already taken a lot of liberties. I didn't write out 230,000. You know, we all know that now I'm talking about thousands. So this graph, the y-axis population in thousands. Now you see why people do things like this data is in thousands. Why do they do that? Because they're lazy. You don't want to write out all those zeros, right? Furthermore, this is all in years. That's 1970, 1980, but I didn't bother writing it all out because, again, I'm lazy. No, I'm not lazy. But you're allowed to take certain... Okay, so now let's plot it. In 1970, the population was 197,000, so that's about there. In 1980, the population was 212,000, that's about there. In 1990, the population was 215,000, which is just a little bit above it up there. And in the year 2000, the population was 227,000, which is up there. Is my data a perfect line? No, that'd be very surprising. That would be like some really good Planned Parenthood if the population was exactly a straight line. So, well, I can nevertheless draw a line of best fit. So you all go ahead and draw a line of best fit too. So a line of best fit, and it basically tells us what we already knew, which is that this population is increasing. So why we care about a line of best fit is that now I could predict what the population is going to be in the year 2010. My prediction will be the value from the line of best fit. Is that prediction going to actually be the population in the year 2010? No. But it's going to be really close. It's going to be really close, that is, if we trust the model. Okay, so now that we just did all by hand, now we're going to do it by calculator, and we're going to have a lot of fun. So everybody, turn on your calculator and go to, you can see it better if I put it here? You can see it better if it's here.
No.
Okay, put it here.
I can see it.
Okay, so you turn it on, you hit clear. Everybody, we're just on the normal calculator screen. Everything is empty. First thing we're going to do is y equals, right above it, it says stat plot. You have to hit second y equals to go to your stat plot. So it says stat plot, very first one, plot 1 should say off. We want it to say on. So go ahead and hit enter, and then you'll see on, off. And just move the cursor to put it onto the on and hit enter so that it does say plot 1 is on. Down below, you want to make sure that the type is the first type, which is just a scatter plot of dots. Below that, you want to see X list, L1, Y list, L2. So make sure all that is correct. Is that what you see? Omar, you good?
And I just have a bunch of people.
Oh, that's fine. Yours might be a little different. Hector, you got all that? Is that what you see? Oh, yeah, thank you, Lee. Lee can walk around and help him with
This
that.
is on.
Do what, Hector? Okay, good. Yeah, perfect. That's great. Although we want not a line, we want a scatter plot. It'll look better if it's a scatter plot. So hit enter. There you go. Okay, everyone, provided you have all that set up, we want to exit out of that screen. So if you hit second mode, above mode says quit, just hit second mode and you quit and you go back to your normal screen. Okay, all right, so next we want to actually put in our data. So to put in our data, we're going to hit the button called stat, which stands for statistics, of course. So you hit stat, and then you have 3 options, edit, count, test. We're going to do edit. So if you hit enter for edit, you will see now L1, L2, L3. What does L stand for? List. List 1.
Under, is there supposed to be like a 2 in ink?
Well, so it should be blank. So is it blank or do you have things? So blank, blank. You've got some stuff. If you have anything there, push your cursor up so that it highlights L1 and hit clear and hit enter and it will clear out your list. Again, move your cursor up to L2, hit clear, hit enter, and your list will disappear. You got that good? Okay, Omar, you're somewhere for that?
Oh, yeah.
Okay, super. And Hector, you're set? Okay, so now let's enter our data. Our data, we're going to enter the x-axis and then the y-axis. You have to type it all in. So you're going to type in first under L1, 1970, 1980. You just hit the number enter. Hit the number enter. 1990 enter, 2000 enter. Not yet. Well, we don't have any data for 2010.
Oh, yeah.
Yeah, so we cannot put in any data for 2010. Okay. So now hit to the right. And now you're going to type in all the population, all of it, the full value. So 197,200, 212,300. Okay. So when you're done, you'll have a nice little table of values with all of your data. Oh, it was a Gauss. Oh, no, was it gold? All right. So, does everyone have their data? Once all those data points are there, the next thing we want to do is look at that. We want to see the data. So if you hit zoom, one of your options under zoom, if you scroll down a little bit, you get to zoom stat. Zoom stat means it's going to show you exactly the window that has your data. Hit enter, and bam, you've got your data. Isn't that cool? You have to hit zoom stat. Zoom stat. Did you turn on your plot? Your plot is off. We needed to turn that on. So now on. There you go. Now you're ready for zoom stat. And you? Oh, gosh. I don't know how to do this. Oh, you see your plot is off. So you hit enter and then turn it on. And now you get zoom stat. Did you get it, Melanie? Okay. Does everyone else have it? Omar, Gabe, Hector, everyone has it? Okay, so fantastic. We have our dots, but now we want to actually calculate something about it. We want to calculate the line of best fit and we want to calculate the correlation coefficient. So now we go back into stats, and this time we are going to calculate something. We are going to go down to linreg, linear regression, ax plus b. You'll notice they say ax plus b, but that's really mx plus b. It's a straight line. So hit enter. It takes you back to normal calculator screen. It says linreg ax plus b. Hit enter again. So when you hit enter again, it gives you a little table. It says linreg y equals ax plus b. And it tells you that a is 936.31. That's the slope. And it tells you b is negative 1645322.6. That's your y-intercept. So did everyone get?
You got an A plus B equation.
Well, there's actually both options on your list. So yeah, you get the same answers. I don't know why they give two different options, but it's the same.
Well, it's A is like your slope and then B is your.
Yeah. They switch it. Okay, did everyone have it? Gabe? Omar? All right.
So B is the y-intercept.
Yeah, B is the y-intercept and A is the slope. Yeah, now you go to stat, and then go to calc, and then go down to linear regression, and enter, and then enter again. Oh, you just keep hitting enter. Enter, enter, enter. There you go. There you go. Okay, so everybody, let's see what we just found out. We just found out that the line of best fit is the equation y equals 936.31 x minus 1645322. Put that on your graph. Okay, that's the linear regression line of best fit. So the first question, A, find the least squares regression line. There it is. Comment on the goodness of fit. Pretty good. Interpret the slope. Positive, because the population is growing. Now here comes the fun part. This is, again, you're imagining you're the mayor of the town, you're the governor of the town, you're on the city council. You want to take care of the city. You want to be mindful of what's happening, how much infrastructure you have to build and grow. So when you have a function, and our function is f of x equals 936.31x minus 1645316. Remember, there's only two things you can do with a function. What are the two things you can do with a function? You can plug something in,
Plug it in or solve the
set it equal to. Yeah, so that's it. Those are the two things. So look at question B. Use the regression line to predict the population in the year 2010. Now, what is the year 2010? Do I plug it in, or do I set it equal to? You plug it in, because what is my input? My input is time. So I'm going to input 2010. So I literally just go ahead, you can use your calculator, you're going to input 2010, you're going to do this times 2010 minus that. So you're going to do 936.6, sorry, 31. Times 2010. Minus. And I got 236,660.5. So that means that we predict, according to this linear regression model, that in the year 2010, there will be 236,000 people. Now you'll notice the problem tells us the actual figure from the census was only 230,000. So this was predicted, and the actual was 230,000. So how good is that? Yeah, I mean, it all depends on who you talk to, right? I mean, that's fairly close. I mean, 230,000 versus 236,000. We're talking about a difference of 6,000 people. Now, 6,000 people could mean a lot. You know, that could be, that's 6,000 more apartments, more homes, more grocery stores, more supply, more water supply, more waste management. So, I mean, that's, you know, who knows if your city can just automatically accommodate an extra 6,000 people, or if you might have to build some more. You might have to build some more housing. You might have to build, yes, build some more grocery stores. Well, there you go. Okay, so now second question, part C. Use the regression line to predict when the population will reach 250,000. So 250,000 is population. Do we plug it in or set it equals? Set it equals. So you take your whole function there, you set it equal to 250,000. Now I'm going to tell you something right here. Don't quote me on it because I'll deny it. I won't even write this down. I'm just going to do the whole thing in my calculator, right? Because I know that to solve for x, I have to add the 164 number over and then divide by the 936. So I'm not even going to write anything down. I know, which is very, gosh, what's the word? Not showing work. It's like,
Lazy.
Lazy, what's the other thing? I was going to say sacrilegious. Like, whoa, like, perish the thought. Don't solve the problem without writing anything down. But in this case, 200, we have to do all of our calculations on the calculator anyway. So 200,000 plus the 164. And then, now make sure you hit enter. You don't just write that plus that divided by that, because then your calculator will think that you're dividing this by this. You have to do this plus this, enter, divide by that, enter.
Round to.
You can also put parentheses as well.
Or you can do the parentheses.
Round to the nearest year.
So, yeah, now we got 2024.246. So, I mean, yeah, you could round. Or you could try to calculate what month that is, which is really fun. So if you subtract the 2024, then 0.2 times 12 months, this is really the second month, so that's February. And then subtract that out times 28 days, that's the February 26th. And subtract that out, multiply by 24 hours a day, that's at 22 o'clock, which is 10 p.m. And then you can keep going and say, well, what time exactly is that? That's 10:52 p.m. I'm just having fun. I'm saying, you can turn a decimal that represents a year into a precise thing, which is fun to do. Yeah, exactly. Okay, so there we have it. So what year will the population reach 250,000? That year, 2024. So again, as a city planner, that's helpful information because you're saying, okay, well, we only have 227,000 people right now. We need to be able to accommodate 25,000 more people. So we need to build more roads, more stores, more housing, more everything. That is, if this model is meaningful. Because maybe there's just been a spurt in population lately, but maybe maybe the town is really decaying and all sorts of people are going to start moving away. In which case the population is not going to keep growing, the population is going to go down. And then you wouldn't want to use this model at all. Like if the next couple data points that you had actually look like this, then what kind of regression would we want to use? Not a linear regression, we'd want to use a quadratic regression. And that's an option in your stat. If you go click on stat again real quick, you have, go to calc, there's quad regression, option 5. So you can do quadratic regressions, cubic regressions, quartic regressions. You can try to fit your data to any curve you like. Okay, well, I hope you enjoyed that. It's kind of fun to be able to take
EWR.
what?
EWR.
That's a power function. So like x to the n, it'll choose the correct.
Would we do?
What?
And would we do?
No, it's just representing a letter. I mean, it's just representing a power, like x squared, x cubed, x to the 4th. It'll choose for you which power would be best. Okay, so everybody, that next question there is just like the one we did, number 2. So let's go look at number 3. And it's great reading out time. So number 3, first of all, notice, sometimes when you read a math problem, they talk about things you have no idea what it is. And so your job is to go find out what it is. So right here it says, using the energy production data given below from the years 1950, 60, 70, 80, 90 to 2000, the production in quads. What is a quad? We're looking at energy production in quads.
4.
Yeah, sure. Quad means 4. Like a quadrilateral is 4 sides. But why on earth? What is that? Has anyone ever heard of a quad? So what you'd do is you'd go to Google and say energy production quads. And you'd say quad, Wikipedia. It says here a quad is a unit of energy equal to 10 to the 15th, which is a quadrillion. That's quadrillion BTUs. Now this begs the question, what's a BTU? But just for now, we know that a quad is a unit of energy that is a quadrillion BTUs. So what is a quad? Quadrillion BTUs. And some common types of energy approximately equal to one quad is 100,000 million billion. 8 billion gallons of gas. Okay? So that's what a quad is. One quad of energy is equal to 8 billion gallons of gas. Right? So how many of you have ever put in 8 billion gallons of gas into your car? Probably none of you, right? Not even in your lifetime. Yeah, but if you can imagine 8 billion gallons of gas, okay, at like all the gas stations in all of the US, you'll probably...
I did, but it was an SUV.
Yeah, maybe it's an SUV. Eventually, you could get up to a quad. Okay, so that's what we're saying a quad is. How much energy is a quad? 8 billion gallons of gas. So it's a lot of energy, right, folks? That's a lot of energy. Now, notice, it says right here, the global primary energy production in 2004 was 446 quads. Okay, I want you to appreciate that. How much energy did the whole Earth produce in the year 2004? 446 quads. So just imagine how many quads were made in the year 2004? Only 446, right? So that's what we should be thinking in terms of comparing this to something. So now let's look back at our data. And let's just kind of write something there on our data. On your data, right over here, near the 71, just right here go global 446 in the year 2004. All right, so in the year 2004, which is often close to the year 2000, the whole Earth was only 446 quads. So who do you think this represents? Because they sure didn't tell us. Who could produce 71 quads if the whole Earth is producing 446? Yeah, maybe China, maybe the US. You know, I wouldn't be surprised if it was the US, because they normally do try to take this data from real sources. So they could just be talking about the US. They could be talking about North America, US, Canada, Mexico. Or maybe they're talking about China. Who knows? But who are we talking about? Either one big country or maybe a couple big countries, right? So now we actually, what's that?
Perhaps.
The who? Yeah, the whole continent, right? So now we have some context, right? We have some context about what we're talking about. We're talking about energy production, probably for North America or just the United States. Because what is that fraction anyway? 71 out of 446? That's 15% of the whole world energy production. So that's what this problem is talking about. So now let's look a little closer. Do we want to do that graph by hand? You could. Let's just put it in our calculator. So everybody, go back, hit clear. So you're cleared out your calculator. Let's go back into stat. We have to go into the stat. We're going to go edit. And then we have to edit those lists. So again, hit up arrow so that you're highlighting L1 or L2. Hit clear, enter, and it will clear out that whole list. And then move over, go up again, hit clear, enter, and it will clear out that whole list. So you've just cleared out all your data. And now we're going to type in new data. So again, your first column, L1, will be all the years. So type in 50, 60. Okay. So you have all your data for all your years. And now go over and start typing in those quads. So now we have all of our data. What do we do next? Zoom. We're going to zoom stat. So we're going to go down here, zoom stat, hit enter, and you should have some nice data to look at. Now, you also have already graphed your linear regression line for that previous problem. So if you want to now, hit y equals and clear out whatever line you had already graphed, your line of best fit. And then you can just go back and hit graph again, and you're still on your data. So if you just hit graph, or it's zoom stat, yeah, there you go. Okay, so is everyone looking at their data? The data doesn't look so good. What happened? Go to stat, and then go to edit. Yeah, enter.
Did I make a mistake?
Sure isn't. So that one data point is way off. So we're gonna edit, and that's because you didn't put in a decimal point.
Oh.
Okay, we have 5 minutes. Let's finish this problem. Did you get your data? Hector, did you get your data? Oh, go ahead, type it all in. Yep, very nice. You got yours? Yep, very nice. Yeah, outliers. Just so you know, that's what it's gonna look like. But
I've
you
got
go.
points too.
You have different points.
Yeah. Well, I mean, I'm but points the first two. I'm guessing mine's just a solid on.
Oh, yeah, that's right. Okay, Valeria, did it work?
There you go.
It worked. It worked. That was a.
Got it.
Okay, yeah, perfect. Okay, so folks, once you have your data, we want our line of best fit. Now let's go ahead and hit stat, and then calc, and then linreg. Stat, calc, linreg. You gotta go down to linreg. Now this time, you'll see that your line of best fit is 0.758. I'm just gonna use the first couple decimals, minus 1439. Is that what everyone else got?
That's right. This is really different, like, the A is one.
Yeah, that's fine. It's just flopped.
Oh,
But
okay.
it's still the correct formula. Okay, so everyone, you got this formula. Now I want you to go into y equals, and I want you to graph that line of best fit with your data. So y equals, and actually plot that, so 0.758x minus 1439. You can tell I'm rounding quite a bit, but that's okay. And what you'll see is that the first two data points are super different from the later data points. And because of that, your line of best fit really sucks. Right? It's not a very good line of best fit at all.
So what did you do?
Once you have those numbers, then you go to y equals, and you type it in.
Oh.
Yeah. Did it work? You graphed it? Yeah, very good. You graphed it? Okay. Omar?
When we do the line, do we start from 0? Because that's what mine did.
Yeah, no, that's fine. Yeah, what do you mean start with 0?
Because they start at 0, like the line, but you start at.
That's not at 0, 0. This is zoomed in, and it's showing just one portion of the graph.
Oh.
Yeah. Okay, so everyone, let's look at this next question. It's very interesting. So first of all, plot the data using the graphing calculator and explain why it does not appear to be linear. So what do you think happened between the 60s and the 70s that global or this energy production changed so much? Well, the Industrial Revolution, I think, was like the late 1800s.
Yeah.
But between the 50s, the 60s, and the 70s, what type of new energy source did we come across?
Oil.
We've had oil for a while. Nuclear energy, right? Nuclear power. Okay, they invented the H-bomb, the atomic bomb in the 50s. So we started getting nuclear power plants, and so people were able to generate energy in a completely different way. Okay, so you could just say new technology. Why is it not linear? Because there was new technology advanced between the 60s and the 70s. Next question. Why would ignoring the first two data points be justified from a historical perspective? Are we still generating energy the way we did here? No. We have new technology. We're generating energy the way we are here. So we would look at these and say, these are outliers. Forget that. That's a different time. That was a long time ago. That was before nuclear energy. So instead what we would do is delete those two data points. So now let's do it. You'd go into stat, you'd go to edit, and you would just delete. You'd hit the DEL button, delete, delete the top two data points. Delete, delete. Now we're going to have just the data points that are up here. So I've now deleted those points. And now we can get a new line of best fit. A new line of best fit. So
What was the answer for A?
it does not appear to be linear because there was new technology between the 60s and the 70s.
So it's not appear to be linear.
Well, it says, why does it not appear to be linear? It's definitely not linear. You would say new technology. Okay, so now let's find the least squares regression for the last four data points, and now talk about how good that is. So now you do this stat, calc, linreg all over again. Stat, calc, linreg all over again. And now we have the formula y equals 0.266x minus 459.86. And now if we go back to y equals and type in that line, 0.266x minus 459.86. Now, your line of best fit is awesome. The line of best fit goes right through those 4 data points, looks really tight, and the correlation coefficient is now excellent. Yeah. So that, oh yeah, you got 2.266. So you go to y equals, it's 0.266. Now you have it.
Okay, oh, it's always.
Yeah. Now, I think you hit zoom again, didn't you? You hit zoom because you zoomed in on just the 4 data points. I did not hit zoom, and it just shows me what the original graph was.
Oh, yeah, because I got rid of the.
If you got rid of the 2 points and then hit zoom, right?
Yeah, well, I got rid of the.
Oh, okay, yeah, and that's why you zoomed in. I'm just saying that's why our graphs look good. Okay, hey folks, I realize class is over now, so do your practice test, go online, see that I posted the solutions to everything. Know that when you come back on Monday, we have our test. You have the entire class period to take your test. You get to use your calculator, but no notes. And if you have any questions, please come ask me. Please email me. I'm available all weekend long.
So I just need to use a late pass on something that's already.
Oh yeah, let me show you.
Because yeah, in mine it doesn't let me.
Right, right. Once you pass the due date, it won't let you do it.
So this is the graph that I got.
So what you need to do is go into y equals, and you have to change that function. So if you put the 0.266 and then the other thing, which was what, like 900? Then you need to go get the actual
Yeah.
numbers. Yeah.
Okay, perfect. Thank you.
You're welcome.
I know today, so.
Gabe, I'm almost ready.
Oh, no worries.
Gabe, please stop rushing me.